So we're finally on the last part of this module, which is polyprotic acids. And the acids that we've been dealing with up to this point have been monoprotic acids. Monoprotic acids. Which, if we break down the name, mono means one. Protic is just your proton. So that means that essentially we've been working with one proton acids or one hydrogen acids, meaning that they only have one hydrogen. So take, for instance, hydrochloric acid, hydroiodic, acetic acid, which with acetic acid, it's this H that matters, not this one, because that's just for our methyl group. Not these three, they're for the methyl group. Yeah. So then, essentially what a polyprotic acid is, polyprotic acid. So poly means many, and like I said, protic is your proton. So a polyprotic acid is a many proton or hydrogen acid. So if you take, for instance, your carbonic acid, which is H2CO3, or your phosphoric acid, which is H3PO4, you can see that you have more than one hydrogen in it, hence the polyprotic name. So, what does it mean to be the polyprotic acid besides it having many protons? So what happens because you have so many protons, it means that you have more Ka values, meaning that you have more than one. So essentially you have as many Ka values as you have hydrogens. So then take, for instance, your carbonic acid, you have two hydrogens, so you would have two Ka values. Phosphoric acid, you would have 3 Ka values. And what's going to happen with your Ka values is that your first Ka value is going to be larger than your second Ka value, which is going to be larger than, let's say, your third Ka value. And why is this? So essentially, remember what we mean that a large Ka equals a stronger acid. And for it to be a stronger acid, it means that it dissociates more easily. As in, it'll let go of the hydrogen easier than, let's say, if you had a really small number. Like, that means that you're dissociating a very small amount at any given time, right? So it's kind of with your hydrogens, you can think about it kind of like money. Like if someone asks to borrow $1 from you, you're going to be like, yeah, fine, it's $1, like here you can have it. But if they keep asking and asking and asking, it's going to be harder for you to let go of that dollar because now they're asking too much of you. And it's essentially the same thing with polyprotic acids, hence why your Ka values get smaller and smaller because it's harder for them to let go of that hydrogen. So, yes, that's essentially what it means to have a polyprotic acid and why your Kas are smaller. So then, I'm gonna scroll, because I keep forgetting that I can scroll in OneNote instead of erasing, but that's just, I keep forgetting. So then we're gonna do an example for finding the pH of a polyprotic acid. So let me just, example. So then we're gonna do, to find the pH of a 1.6 carbonic acid, well 1.6 molar carbonic acid solution, given that Ka1 is equal to 4.2 times 10 to the negative 7, and Ka2 is equal to 4.8 times 10 to the negative 8. So we're going to set up our equation, which is going to be H2CO3 aqueous plus H2O liquid. And since this is still a weak acid, we do our double arrows, and we're going to end up with HCO3 minus plus H3O plus. So we set up our ice table where initially we have 1.6 condensed state, okay, aqueous, we have 0 and 0. Our change, minus x, plus x, plus x, so at equilibrium, 1.6 minus x, and x. So then we set up our Ka, which is going to be Ka1 because it's one hydrogen has been taken away. 4.2 times 10 to the negative 7 is equal to x squared over 1.6 minus x. So then this value is small enough for us to disregard this x. So we just go ahead and solve for our x, which should give us, oh my god, that equal sign, I'm so sorry. I'm looking at my notes. Equal to 8.2 times 10 to the negative 4. Yes. So then we basically solved for our HCO3 as well as our H3O plus here. But we're not done yet because now we have to remove this next hydrogen. So then we carry on to our next step, which is HCO3 minus plus H2O, still a weak acid, yields CO3 2 minus plus H3O plus, and our initial now is going to be 8.2 times 10 to the negative 4. I just realized that looks like a 9. I'm so sorry. That's a 4. Let me erase this and make it prettier. To the negative 4. This doesn't matter. This is 0. And this is also going to be 8.2 times 10 to the negative 4 because we still have some hydronium here in solution. So then our change, minus x, doesn't matter, plus x, at equilibrium we have 8.2 times 10 to the negative 4 minus x, and then 8.2 times 10 to the negative 4 plus x. So then we set up our second Ka, which is 4.8 times 10 to the negative 8 is equal to 8.2 times 10 to the negative 4 plus x times x all over 8.2 times 10 to the negative, times 10 to the negative 4 minus x. So then it's the same thing as before, where this is small enough that we can disregard this x as well as this plus x, because it's insignificant that if we were to add it, we would still have the same exponent. So then we're left with 4.8 times 10 to the negative 8 is equal to 8.2 times 10 to the negative 4 x all over 8.2 times 10 to the negative 4. These numbers are the same, so they cancel. So essentially your x is going to be equal to your Ka most of the time, well, your second Ka. And then if I wanted to find the final concentration of all of my products, then I would just add or subtract x to all of them. But, okay, so here's the thing. I didn't want to say this because I wanted you guys to go through this whole problem with me. But this number is so small, like it's to the negative 8, right? That if I were to add it to this number, then it would be still the same number. So we could solve for pH after the first after the first hydrogen is removed, essentially, because these next numbers are going to be so small that they won't affect this value at all. So pH is equal to the negative log of 8.2 times 10 to the negative 4. So our pH is equal to 3.09. So what I'm saying is essentially for you guys, since you guys do have a multiple choice exam, is that if you get a polyprotic problem, you can just take away the first one, like the first Ka, and just solve from there, because these next numbers are going to be so insignificant. But if it is asking for final concentration of either the carbonate or the H3O+, you're going to have to solve both or all 3 Kas for it. But yeah, this is kind of a shortcut, is that the numbers are usually insignificant enough that if you were to add them, your exponent would still stay the same from the first one. So yeah, so you have a pH of 3.09. Okay, so we're going to do one other example of these, because sometimes the problems aren't so nice where you can disregard the x's, you know? So let's scroll down some more. Alright, I'm going to erase this part. But okay, so let's do another example where, for instance, let's say that we're finding the pH of, what is it? 3 molar oxalic acid, okay, I don't know how to pronounce this, but it's H2C2O4, and Ka1 is equal to 6.5 times 10 to the negative 2, and Ka2 is equal to 6.1 times 10 to the negative 5. So then we're going to write down our first equation, which is H2C2O4 yields HC2O4 minus plus H3O plus. And initially we have 3 molar. Okay, I forgot to put the water, so just assume it's there. 0 and 0. Okay, since I forgot to put the water, I should just change this to H plus. Yeah. So then this is going to be minus x plus x plus x. So at equilibrium, we have 3 minus x, x, and x. So then we're going to do our first Ka, because we removed our first hydrogen, 6.5 times 10 to the negative 2 is equal to x squared over 3 minus x. And okay, so remember how I said it has to be either smaller than negative 5 or 1,000 difference between our initial and our Ka in order to disregard the x? Well, in this case it's not, because it's negative 2. There's not going to be 1,000 difference between a whole, like, one number, like 3 divided by this. It's not going to be 1,000. So we have to do the quadratic formula, which I know, it sucks. But basically we're going to do 6.5 times 10 to the negative 2 times 3 minus x is equal to x squared. So we end up with, where's my math? Okay, 0.195 minus 6.5 times 10 to the negative 2, x is equal to x squared. So 0 is equal to x squared plus 6.5 times 10 to the negative 2x minus 0.195, which if you guys are wondering why this turned into plus and this to minus, I just moved everything to this side of the equation to leave my x squared positive. Okay, so this is going to be my quadratic formula. Well, it's going to be my quadratic equation. And then I'm going to plug it into the quadratic formula, which is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, which if you guys don't remember, whatever your coefficient of x squared is a, this is your b, and this is your c. So we're going to plug all of that into the equation. So 6.5 to the negative 2 is equal to 0.065, so that's what I'm going to write it as, plus or minus 0.065 squared minus 4 times 1 times negative 0.195 all over 2 times 1. So you're going to end up with negative 0.065 plus or minus 0.88 all over 2. So then we want to get our positive answers, so we're not even going to do the minus because that'll give us a negative number and we can't have a negative concentration of something. So then when we do this, you should get your x value to be 0.41 or around there, depending on rounding, right? So then that's going to be our x value. So like I said, shortcut, these numbers are going to be insignificant enough that we can just figure out our pH from here. So pH is equal to the negative log of 0.41, which is equal to 0.38, I believe. Let me double check my work. Negative log of 0.41. Yeah, 0.38 is our pH for this polyprotic acid. So then if this problem had asked us for the concentrations of everything like final, then we would have to solve for everything else. So we would move on to the next step, which would be C2O4 plus H2O, because this time I did remember the water. So we would end up with C2O4 2 minus plus H3O plus. Initial, we would have 0.41, doesn't matter, 0.41, change, minus x, plus x, plus x. At equilibrium, we would have 0.41 minus x, x, and 0.41 plus x. We solve using our second Ka, which is 6.1 times 10 to the negative 5 is equal to 0.41 plus x times x all over 0.41 minus x. We can disregard these, and then those cancel. So 6.1 times 10 to the negative 5 is equal to X, and that would be your concentration for C2O4 minus 2 would equal 6.1 times 10 to the negative 5. And then, like I said, this is such an insignificant change that even if you were to do 0.41 plus your 6.1 times 10 to the negative 5, you would still end up with 4.1, well, not 4.1, with 0.41. So your final concentrations of everything else, so like your H3O plus ion, would be 0.41 molar. So yeah, like I said, multiple choice, figure out your X value using your first Ka and plug that into your pH equation, and you should be good. So yeah, that's pretty much it for polyprotic acids.